it's my pleasure to have Bowen Zhou here. Bowen comes from IBM. He's currently a program director, managing teams in IBM Watson and also IBM research. And Bowen has done research in sort of a wide range of fields. So you guys might know him as someone who's done work in speech recognition and machine translation, and speech-to-speech translation. For example, his DARPA Transbank project was a very impressive thing back in the days before we had iPhones. But he also had one of the first papers, I think, on deep learning for MT in 2012, which I think people don't cite enough. But now he's working on sort of new frontiers in question answering and deep learning. And, I should also mention he was also a technical advisor to the VP of IBM Research before. So he has a very, very sort of business perspective as well as a research perspective. I think that will show through the talk, and hopefully that will be interesting, especially to students here.
Right. Thanks a lot, Kevin. It's really my pleasure to be here. As I told Henrik this morning, I have always wanted to be here since I was a graduate student. I have two plans. I want to come here for part of the CLSP summer workshop, and I also want to give a talk here. But I guess I didn't realize I could give a talk without doing a seminar, without doing a workshop. But I promise, I will come back for a workshop someday, or send somebody from my team to be the part of the workshop. Okay, so today I'm here to tell you about some work we did for, question answering. Particularly, I want to focus on the recent progress we made on the deep learning space for question answering. So, at IBM, Watson, our journey starts with question answering, right? So this is a picture many of you recognize that we won the Jeopardy competition back in 2011. That starts the, our mission to build an AI platform for many businesses. But soon after Jeopardy, many clients from different industry came to us, say, can you build the same system for us, but not answer Wikipedia questions, but answer the questions I have in my business? And it turns out that's very hard. It's almost impossible to scale to all many industries with similar performance like what we see in Jeopardy. So later on, we formed this Watson group, and we changed the business mission to, I'm not changing, we are adding another business mission here, is that how can we enable the AI techniques you see from Jeopardy, make them look like a platform so people can build on top of that. So that's what we rolled out last year called the Watson Developer Cloud. So the key idea here is that we want to build a number of AI core technology and the capabilities, hide them behind APIs, so people can build, their own applications of their own problems on top of these APIs, right? So many of this work you probably recognize, from, my colleagues at IBM, lots of people work on speech recognition for many years, so there's a service there, TDS, there's a machine translation APIs, from our translation team, which I have been part of with both speech team and the translation team. And we also, from my team, I built after I joined the Watson group, coming from the natural language classifier, retrieval lang, and also many other language APIs. I'm going to mention some of them. They also have work on from relationship extraction, vision, other APIs. But I'm not here to tell you about this, although in case you guys building startups in the future, those are some numbers you can take a look. We have been roll out this cloud platform only less than a year, but I think we're getting attention, getting some attraction. So this is a number from last year, and not the newest number, but from my colleagues. We have more than 80,000 developers worldwide building applications on top of that. We have seen more than 10,000 applications calling one or many of these APIs behind these applications. We have about 3 billion API calls per month at this point. Our partners, that's one thing I want to mention here. The partners are these guys, either coming from a big business or coming from a small business, but they are building some of their applications, work with IBM. I think the model is the free charge until you getting your own revenue. So that's why this attracts lots of startups, because you don't have to pay anything up front until you turn this into profitable business. Okay, but I'm not going to talk about this. I want to go back to question answering, right? So I want to tell you why we are obsessed with question answering. for my team and also for IBM also in general. Because, question answering today, it's everybody recognizes a very complex, very insightful AI application. But the point I want to make here is that this is one of the few AI applications that actually can do IA. What I meant by IA is, intelligence augmentation. So this is something not competing with human, like you play AlphaGo. This is more like getting human getting smarter, right? So how do we people learn? I mean, while every kids learn by starting asking good questions and get them answered. So you can learn from insights from your parents, from your teachers. That's how you grow. So in the future, we probably can let this kind of AI techniques to help people grow faster, grow more exponentially. That's a help, right? But the point with QA is that at every interaction between human and the machine, both sides learn something. So that's why I feel like it's a very, very, pressing problem for us. And also, people also claim now everything is, it's a QA, right? You can say translation is a QA because you're asking what's the translation of this problem. But I will tell you more, there are different kind of QA problems. It's also kind of risky to claim everything is QA. We need to be very careful to say, what we are talking about when we define QA, because the QA is bigger space. So, as you can all recognize, QA depends on a number of different technologies, right? So this is by no means is complete. It requires many more techniques. That's why QA by itself is a driving force for many other techniques to mature and to develop. Given QA is so complex and it's large space, I think it's fair for us to claim, we as a community only scratch the surface of QA. QA is too complex, and there's no QA system can answer all questions, and I don't see it possible in the next few years. So that's why at IBM, our focus here is that no longer trying to only build like a Jeopardy-like system to answer all questions even in one domain. We're trying to focusing on enable massive developers out there to build their own QA systems for different industry applications, different use cases. Right? So I think that's more practical goal, given that genetic QA won't be ready anytime soon. And the point here is that we want to enable 80% of the developers out there to do some kind of QA, and we also want to give them something 80% is already done. They only need to add some layer on top of that to stand up their own applications in QA domains. Okay. So to achieve our goal, we actually need to understand what exactly QA really is about, right? So I think, as I said, QA can be claimed very, very broad. And there are also different kinds of QA problems. People in the past, try to categorize QA into, for example, factoid QA versus non-factoid QA, right? Factoid QA, you are looking for this categorization is based on the answer type, right? Factoid, assume your answer is like looking for an entity or relationship. Non-factoid QA, your answer is more like a passage, a paragraph of documents, right? So that's one way to look at it. Another way to look at it here is that people looking from question distributions. You can say this is a head distribution QA or long-tail QA. My view here is I try to bring another perspective. This is based on what we observe in the real-world problems, what kind of problem people are building in their applications for QA, right? So there actually can be three categories. The first category here is that for these applications, your answers, your documents are already categorized, already curated. So this problem of QA can be reduced to understanding questions. Sometimes even can be reduced to just classify questions. This will get the problem solved. I will show you some examples. This actually sounds simple, but this covers a wider variety of real-world QA problems we have seen in the developer space. Then the second part of category of QA is that your answer is somewhere. The answer could be a passage answer for non-factoid QA, or could be a supporting evidence to support your factoid QA. It's somewhere, but you don't know where it is. You don't even know what should be the right length for that answer. You don't know where should start, where should stop. It's all of somewhere. So to this kind of QA, you need to understand the questions, of course. Always you need to understand the questions, but also you need to understand the contents. You need to make sense of contents. You need to also have some domain knowledge. You need to also understand the context. But you sometimes you also need to generate the answers, right? Because the answer could be there, either too long or too, fragmented. When you understand the content, you should consolidate them together to form up some answers. That's the second category. There's even third category is that, you're asking a question open-ended, or even if it's not open-ended, the answer does not exist anywhere, or you don't know that. It makes it somewhere, but you don't know. You're not sure. You need to go through your content, go through your knowledge representation. You need to infer the answer. You need to do deduction. So in this case, some of the system you need to have reasoning capability. You need to do reading comprehension. Also, you need to generate the answers in this case, right? So, by the way, for some of the reading comprehension tasks people have seen in the papers, I don't believe that in category 3 because the answer still assume, for example, entity in one of the articles. So in that case, I would categorize them into the second part. But anyway, so you can see that that's my view how to categorize different QA problems. The challenges, of course, it's growing when you move to 1 to 3. But if you look at the real-world applications, you can see the distribution may not be only focusing on the third category, which is very hot now. So for my talk today, I will briefly cover the first part. I will spend more time talking about the second part. I will also, give you some examples of what we are working on the third category. Because remember, our goal here is not building one system. We're trying to, enable people to build a QA system. So we want to, for every category, we are looking at end-to-end learnable solution. So for the first and the second one, we actually have end-to-end learnable solution. The third one, I think, is still being evolving. People are still using a lot of pipeline-based approach, right? You do information extraction, entity, relation, event. You leverage knowledge graph. You still need that. People are still start doing end-to-end learnable approach in this space, but so far they're all toy tasks. We are pretty far away from a real world system. But I will tell you some work we are doing in this space as well. Jason?
So you don't mention the variant of 2 where the answer exists in a structured database. Or maybe that falls under 1. Is that something that you guys aren't interested in?
Is the answer existing in
structured database?
Yes. So that depends, right? So if for example, if it's a simple QA, meaning you are looking for facts, simple facts, you can find the answer. So that's in the category 2. But if you're looking for some answers that requires you to, train reasoning in a knowledge graph, and also you need to complete the knowledge graph. That's in category 3, in my opinion.
Right. I was asking about category 1.5, natural language interfaces to structured databases. Structured databases.
Yes, I got that. Yes, so that could be 1.5, as you said, but I would think of them also as 3, unless you assume the answer, you already know the answer is already in the database. If it's open-ended, then it will be category 3. If not, maybe it's 1.5. Yes, of course, some problem can be combination of them. Yeah. Okay.
And I have struggled with this sort of classification of the QA task.
Yeah.
Take something like the Jeopardy game. Right?
Yes.
If you look at the game, it looks like all questions are of the factoid type because the
Yes.
answer is usually just a phrase or a name.
Right.
But behind the scenes, you actually have to do a lot of reasoning and things like that.
Right.
The nature of the question is rather unpredictable.
Right, exactly.
So where would you put that? Would you put that in 2?
Jeopardy, I will put that in 3. Because again, I'm not looking at the answer type. Answer type could be factoid, could be non-factoid. It doesn't matter. As long as you are not certain. Do I have a corpus content that answer? Do I have evidence for that answer? And my answer need to come from a reasoning step. Then that is 3. But that's the problem definition. But the approach-wise, you don't have to do reasoning. I mean, people can still get a pretty good system by doing simple information extraction, IR, the entity derivation. They don't have any reasoning here. But that can solve the category 3 problem to some extent. But that's my main point. You can. Using domain expertise, engineering to build a system working very well for particular application. But if you, like what we are doing now, we want to enable others to do this, you're looking for some end-to-end learnable approach. That one, I think, is still ongoing. Yeah, okay. Good questions. Any other more questions? Okay. So now let me quickly tell you, for the simple first category, it turns out that lots of, applications out there can benefit from this category 1. For example, if you're running a hotel business, right? So you won't have a system that can answer all the questions your guest may have, right? So there are many different ways to ask for, hours of your dream operation in this hotel, right? So the point of this business here is that, if you are a hotel employee, I think, in your training, you probably already know the answers to all the possible questions your guest can ask, right? So either within your hotel business, you have a predefined manual to tell you how to answer that question, or it's out of your hotel business. You say, oh, sorry, sir, I cannot help you, or call somebody else to help you. Call 911, for example. Right, so for this kind of application, all you need to do here is understand the intention behind the question, right? So that's exactly, the natural language classifier we built on Watson Developer Cloud is trying to target. And based on that, we built, for example, a demo use case for this is this Connie. Connie is a collaboration between Hilton and IBM on the robot, concierge. So this is actually deployed in DC area. You guys actually can visit him. But the point is that, if you are big guys like Hilton, you can work this with IBM to give you a solution. But how about these small guys? These small hotels. You can do something similar. You can. There's actually a startup using our APIs to build the solutions for all the hotels, right? So, but the online technology is the same. So, again, the key point is this, right? So, key point is we're providing the service to the developers. So, what they need to do here is they can bring their own data to our platform to train their own classifiers on top of our models. So we have a baseline model, we have adaptations, we let them to train their own more classifiers using deep learning. So our service including deep learning training as well as a long time. So the quality APIs to build their classifiers. And the good news here is that the accuracy is pretty guaranteed. We cannot claim always highest, but reasonably high for almost all the use cases we have seen so far out of the box, without any hyperparameter tuning, any feature engineering, any domain adaptation from developers. So I'm not going to talk about more details about this, but we have 3 papers to talk about the technology behind this LC classifier. Two from ACL last year, and 1 from ASRU last year. Okay. Yes.
So you're saying for this type of problem, you just classify the question and automatically, if you get that right, you know the answer.
Yes. Yeah. We assume the developers have the content side curated. Right. So let's go back to my first definition of the first category. So, for example, if you're a hotel, you have actually a menu how do I respond to different clients' question, different question from the guests.
So in practice, how large of a question or answer set?
That varies, right? So we have in our to these clients calling our APIs, we have seen, we have look at their data, right? So we see people actually using this for example, for healthcare, insurance. They are having like 1,000 different categories, as many as that, or a few thousands. Some of us can go as few as tens. So it depends on different applications. The point here is we prove that this classification accuracy using deep learning approach is quite scalable. So we are working well from a number of classes like check data. Our paper talk about check data. They have only six class. Our accuracy is best accuracy is 95.5. We're the best results in 2015. But for 1,000 classes, our accuracy around 85%, top 1 accuracy for their use case. Okay. Question? I'm not sure. Can you speak louder?
How do you handle temporal modifiers?
Okay.
So if you want to know the hours, you're going to say what's the hours of the time.
Okay. So that leave to the developers to decide, right? So if they think their answer is temporal, independent. So I have a unify hours. So that they will categorize all this go to the same category, right? Or they can decide, have hierarchical category. So I will ask you, okay, list about the gym hours. I'm going to ask you, which day you want to go, right? Saturday or, that depends. So that leads to, another point here is that we actually enable people to call dialogue APIs. So in that case, you want to build a dialogue system to disambiguate the questions. So again, here we don't do anything ourselves. We just let them call this API. We give them instructions how to build their applications. How to build that is up to the developers and up to their use case. Okay. All right. So let's move on. So this is outline for this talk. So actually, for today, I'm going to talk about some deep learning work on the second category. Passage answer evidence, identification for QA. I will talk about the 3 main progress we made last year. And I will also share with you an open data set that you guys can do research with and can do benchmark. If you have a time, I will also talk about something scratch face for the third category, which including some work on how do you generate the answers, right? You don't have any answer existing in your corpus. How do you come up with the answer using deep learning model? I will also talk about our learning to reasoning work. Some couple slides just to flash the idea. Okay. Now let me move to a different QA problem. Now, this problem here is that the question can be very simple. You can always answer the question, right? That's Medicare cover my spouse. But to answer that kind of question, you need to understand very well in this domain, and you need to understand your content, right? So the content is too broad, is to be curated, or is too sophisticated. You need lots of expertise to curate it. So the task here is that how can I identify the correct passages in my entire corpus, potentially including verb, to identify the piece of text that could answer these questions. So that's a task. Usually when you do this here, that you need to figure out how do you model questions, how do you model the passage answers, or supporting evidence for factorial QA. Then how do you measure the similarity? How do they match to each other? Of course, in the deep learning framework, the good thing here is that you can combine all of them together into one problem. So, but this is not an easy problem as it looks, right? Let me tell you what we found out from real world applications. The reason for question answering like that, why this is a challenge is that there's a very complex and versatile relationship between question and answers. Depending on what you're asking, sometimes a good answer needs to entail the question, but other times, question need to complete. The answer need to complete the question. So which means what you show in the answer has nothing to do with what you see in the question, at least from the surface side. And sometimes you need to elaborate the question. A good answer need to elaborate the question. Or you need to, rationale. People asking, why should I do that? You need a rationale to this guy, why his decision is good. So that's a good answer, given the context. And some other time, you need to reflect upon part of the, question. So the point here is that there's no single semantic correspondence between question and answer. For if you think about the generic question answering problem. So that makes, if you traditional approach, if you want to design features, how do I match the question answer very hard, right? Because the task varies all the time. So that's why we focus on representation learning approach, such as deep learning, to figure out automatically what's the right way to model question and answer and measure their similarity. But before we start doing this work, we realize there's actually not real good data out there for this kind of task, right? For people, some of you work in this space, for this kind of task, there's a couple public available data sets. One is Check QA, one is Wiki QA. I will mention them in our results. Both are very small. So we actually spend some time, create a data set which I want to share with you for your own research. Is that we did this insurance QA data set. This is so far large scale QA data set in this domain, trying to find the passage answer to questions, and it's publicly available. So we basically this data from insurance website. So that real questions from real human, right? So that they are real end users. So it's not like other QA that people come up with the questions after after the CFAX, for example, and the answers are coming from domain experts. They are insurance agents. And also the answer is not unique. Sometimes you see multiple going to choose answer from different insurance agents. Yes?
The original human-human interaction spoken, or were they by text, like email?
This is by text. It's on the website, yeah.
So the original interaction was also text?
Yes, not much speech there, yes. Michael Piccioni asked the same thing. Yes, we call that data set. So here's the numbers we show. We are contrasting this data set with Track QA. What you can see here is that other data sets is less than 1,000 training questions. So we have we have at least 10 times bigger. And another thing here is challenge here that the answer is much longer than what you typically see, right? So this data set the answer is 40 times longer than question. And the other data set you see is, it's a very, very small length of answers. That always makes this problem much more difficult and harder to train. Okay, so you can download the data set from the GitHub, and we're actually updating this data set on a regular basis to make it better and better. Because we internally use the data set to drive our progress, to measure our progress. Okay. All right, so because data sets, now we try something, baseline approach from deep learning to this task, right? So some tasks, can be very, very, very natural, very intuitive, right? So you have a question, you have a candidate answer. So what you can do here is, okay, you start with word embedding, and then you are trying to build a representation on the question side and the answer side, right? So you can try convolutional networks, or you can try sequential models like a BIOSTM, both directions, right? So you can build a model representation for the question side, for the answer side. So you have Q and A, and then you actually do sort of pooling on this representation. The pooling can vary, and you learn representation in the end for question and answer side. Then you measure their similarity. After that, you do a large margin or minimize hinge loss function to try to train a classifier to understand if this is it's a ranking problem to understand which answer is the best answer to this question, right? So this is nothing special here. People can think of very quickly how we should try to use deep learning to address the QA problems. So we actually put out a paper to try all kinds of basic configuration you can think of. So there's a paper from ASRU last year. We tried different ways of architectures here, sharing different hidden layers, sharing different pooling approaches. We tried like 10 architectures, so we get some results. So that's pretty much basic approach people can think of. That will be our baseline. Our first stop here is to compare. Okay, is that approach reasonable? People can think of, I don't even need a deep learning. If I do IR, how does this work for this task, right? So this is some very quick results to show, right? So if we run this task on insurance QA, we have dev set, we have 2 test sets, right? So you can see that if you only apply more than IR approach, like a Badansky models, you can get around 55% accuracy on top 1 answers that people read them as a correct answer. Using deep learning methods, you can do much better, even as simple as what I just mentioned. So between them, LSTM model works slightly better than CNN model. I think that's not surprising either, because LSTM model can do better sequential modeling. But is this good enough? I think we have 2 observations to tell us it's not good enough, even from last year. So one thing we observed here is that in the real world is that good answers doesn't mean they're perfect answers. Good answers also can be very, very noisy, speaking things that are not relevant to the question. Also, same thing happens on the question side. So then we need some better model to learn how do we ignore part of the answers. So we don't have anything explicitly capture this. Another observation we have here is that good answers must relate to the question, semantically, but often do not show any common lexicons or surface units. So and if you model question answer independently, like what we showed before, right? You model them totally independently until you compare their similarity, then do hinge loss. There's no interaction before the last step. So one thing inside we have here is we should have them interact as early as possible. So that's the motivation we have to improve these models. So I will tell you what we did for this. So based on these observations, we have 3 ways to improve our representation learning for question and answers. The first one here is that we want to do a better representation learning for both question and answers by combining convolutional and also sequential models for the following reasons. We want to leverage convolutional model, which essentially is a bunch of filters. If you think about single processing perspective. So we want to leverage these filters to separate the noise you have from the both question and answer side. And then second, we want to leverage the recurrent models to model the sequence better. So basically, this is a very straightforward idea, is that we can combine the merits of both models together to show better representation. So we're actually going to verify that. The second idea, of course, here is that we mentioned that question and answer should not be independent. So one natural way here to extend to learn from sequence learning model from machine translation is that you need to add some attention mechanism, right? So this is typically in that work, it's attention add on the generation model. This is added to the classification model. But similar thing here is this is one-way attention. We are using attention from a question to constrain your answer representation. The third idea is pretty, I think it's pretty neat here, is that we actually push for the, two-way attention. So you need actually also using your attention from answer to guide your question. So information from both Q and A side should be, information from Q should be used to constrain how do you learn represent A and vice versa. So in this case, we allow them to interact, early in the pipeline rather than waiting for the, last step of hinge loss training. So I will elaborate more about these ideas and show you the results. So the first part is, combining this architecture. So this is straightforward, right? So I'm not going to go to deeper with that, but there are two variations. One variation here is that you actually learn the sequential model first. Then you do a convolution trying to filter the noises on the, hidden states level from LSTM. That's what we call the convolutional pooling LSTMs. Another idea here is that you actually do convolutional first. You're trying to learn how to separate this noise from the original question and answers. On top of that, you build a sequential model to learn the representations of Q&A. So that's first idea.
What do you mean by noise in the first case versus the second case? Are there very different types of noise?
Noise in general is basically we are saying the part present in the answer side or the question side, but not relevant to how to exchange information here. That's what I meant. But in reality, in this model, they may capture different things. You're right. So in this model, the CM more capturing in the low level information that you only look at labeling local context. You can find something like a insert pod, insert pods. You can filter them. Here it's more like you filtering on the subsequences. So it's different kind of noise. You're right. So you can see from the results actually working quite differently. Okay, the second idea here is, as I mentioned before, is that attention mechanism. So this is a one-way attention mechanism. So the idea here is that why learn a representation of a question? The representation of a question here should be weighting how I look at my answer. So in that case, I will basically using a soft way and also dynamic way to align the more informative part of the answers with respect to the question side. So the math here is actually quite simple, right? So you basically measure sort of a matching score between your answer and the question, and then you convert them into a scalar variable using this equation, and then use this one to weighting your answer representation. So these 3W are the attention metrics you need to learn. So what I mean by dynamically is that when you start training. So this alignment model will change based on how do you learn the representation from Q&A. So alignment and Q&A representation are interacting with each other.
So what is T indexing? Sentences, 20-word windows, something else?
Say it again?
What is T?
Oh, T. T is
Windows or something?
T is a word ID, a word index. A word index, yes, at this point, yes.
And so the hidden representation, that T, is a representation of what feeds into that? Is it like the state of the LSTMs going both from the beginning and from the end?
Yes, if you use a bio-LSTM, yes, that's right. Yeah, okay. All right. So let me show you some initial results first before I go to two-way attention, because that's the part I want to spend more time. But I want to just do validation to see how this works compared to people have been doing already using other techniques for QA. This is including a number of different techniques, right? Including other deep learning techniques. So we started with the track QA because that's how people publish their papers on this task. So this is a small data set, but I think it's still informative. So what we can learn from here, there's some results from ACL last year. I think that's from CMU. It's 71 on MAP and 79 on MRR. But the best results obtained by a team actually adding manual features on top of deep learning models. That's the one we highlighted on the first block. So it's pretty good for this task. So if we try, what I mentioned before, it's vanilla QACN or vanilla QA LSTM, we cannot do as good as this model with manual features. But if you're adding, first of all, if you're adding attention mechanism, we actually can do better than that. So this is, without any manual features, we can actually do better than the best model. So that's the first observation. The second observation we have here is that actually the convolution pooling and the convolution-based LSTM actually have different results, but they're comparable. They both help on top of the vanilla CNN or vanilla LSTM, so which means combining this architecture together, that's have provided you something you're not able to capture in the original model, but they are not as effective as a attentive LSTM model from a performance perspective. So I think one explanation here is that attention LSTM, QA LSTM, make it more explicit which punish the igloo. That's one potential explanation. But of course, we are trying to combine them together. You could combine them together, right? But we haven't time to, finish all the experiments. You can combine this convolutional pooling LSTM with attention mechanism. Okay. But now let me move to, but this is not our best results. Our best results are coming up. Go ahead.
I have a level question of
Yeah.
what is the level of which predictive model you use.
Yes.
All of these models, it looks to me like you can evaluate a candidate answer, right?
Right.
Between the question and the candidate answer.
Right.
So I guess that's the key point of that candidate answer pool 38, meaning on average you get 38 answers.
That's right.
What I'm wondering is, when you first get that answer pool,
Yeah.
you may already have lost because none of them
Sure.
contain the answer.
Sure. Sure.
So is there a way to revise these numbers and say, in the cases for the questions for which it was possible to get the answer, this is the MAP and MRR,
Yeah.
and that for the other, and the 10% of the questions, the first stage already failed. Is there such a breakdown? Or, because this assumes
Right.
everything.
Right, exactly. Because this is an academia problem. Right? Academia typically, with all due respect, they're working on artificial problem. So this is exactly the data set itself, as you said, to define this pool size artificially, and also always guarantee the ground truth out there.
Oh, it's guaranteed.
It's guaranteed. Yes, that's what technical about. But you're absolutely right. I mean, the real world problem we have now is that we actually don't know how big the pool should be, and we don't even know are there any questions out there or not. Right. So that's actually one challenge. So that's why we are working on. People did not pay attention here that we're actually working on a model that we actually can output and say there's no answer here. So that's you move to category 3. Remember my 3 categories? That's how you inform each other.
What I was hoping, for example, is that you would tell us that if all the candidates have very small cosine similarities, then your model will actually tell you that it doesn't like any of the answers. But you're saying that doesn't happen because one of them is always...
For this task, yeah, it's always there. Because this is, how people publish papers. Yes, so this is always there. This is also same thing for the data set that we created. This is each other's QA data set. We also make the pool bigger, to your point. But we also guarantee for this task, because, for people to publish papers, we also guarantee out of these 500 answers you have in this pool, you have one of them is the best answer. But didn't mean the second best is not good. I will show you some examples what it looks like. Go ahead.
So if I understand the bidirectional attention model,
Yeah.
If that's how you, was that the right name?
This is a one-way attention model.
Yeah, the two-way attention model.
No, not yet.
You don't have that yet.
I'm going to tell that yet. That what show as one-way attention. Yeah. So let me show you the results on this data set. So this is again, it's a much bigger pool, 500 answers per question, but also guaranteed there's a good one there. So again, so you see the point, right? So we actually can underperform our baseline models, pretty significantly on this data set. So the best one here is 69% on test set, which is like a 14% higher than IR approach. So again, question answer is not the IR problem. That's basically you guys should be all convinced. All right, so now I'm going to two-way attention models. So now go back to the the general architecture I showed you before, right? So you have a question answer representation separately, then you derive large minimum hinge loss training. So what we are introducing here for two-way attention is this: when we learn a question answer representation, we are not pushing to the classification. We're introducing a two-way attention measured by this particular equation here. So this is, you take the question representation, you take the answer representation, you do bilinear transformation, and you squash the similarity by squash function to bound the similarity. So the key idea here is that let's assume you can project your question onto a new space, and you can measure the similarity in that space. And that similarity will be considered as a representation here, in the middle part. You can think this part is sort of the alignment matrix to align, how each part of a question relevant to my answer, and vice versa. So this is a two-way alignment matrix. Then you do pooling. This pooling here is for the question that you do column-wise pooling. For the answer, you do row-wise pooling. And this pooling will become a vector, and we go through, softmax. The softmax we'll use to weighting the original question representation. Okay? So in this case, you can think of that, here's the attention vector. And after softmax, it become a weighting factor to weighting original representation. But your attention here, of course, it's independent. I mean, your weighting factor is independent. So the key idea here is that we want to let the Q and I have a chance to interact before they get fed into the hinge loss training. You get the intuition?
So what you're saying is that when you're looking at a column in big matrix,
Yes.
that essentially corresponds to a row, basically the length of the question.
Right. Right, exactly. You can think of it this way, right? Row is question, and this is answer. So you are
Positions in the question and positions in the
exactly. You have an alignment weight here.
Right, and what you're taking is a dot product in some space.
Exactly, right.
Between
Q and A,
or
yeah.
let's say a dot product between Q and a rotation of A.
Exactly, right. Exactly, yes.
So the Q com and A com, you've got vectors for all the input positions, for all the question positions,
Yeah.
and vectors for all the output positions.
Right.
And there wasn't a similarity between those after a rotation.
After projection, yeah. Yeah.
And then,
You notice the rotation because there's a P.
sorry, I didn't mean a rotation.
Right, exactly, right.
After a some
Right.
transform.
Yes, yes. That's general idea. I mean, what is the best form of this by-way attention is the open question, right? So we actually follow our intuition, try this bilinear transformation followed by nonlinear factors. It turns out it works really well. But is this the best attention mechanism? We don't know. So that's, I think, it's still open. But one thing I can tell you here is that if we try to remove nonlinear squashing function, it did not work as well. So we did try different variations here. But should this itself become more complex model? I think that's an open question. Yeah. But again, you want to make them easier to learn. So I think this model has an advantage. All you need to learn is matrix P. Okay. All right. So let's see how this works. Yep.
P is just one matrix. It's constant for all QA pairs. Does it depend on the Q and the A?
At this point, it's constant matrix.
It's learned like the LSTM code.
Right. It's shared at this point. Yes.
So it's kind of different from retention, right? The normal use of the word retention, where you get a weighting that's dynamically dependent on your input.
No, you're very welcome. Let me take this back. I'm not really sure if the P is always constant. Let me check. I get it back to you. I think it's probably not. Yeah.
But
It's
in
not.
answer to Kevin's question that the attention vectors pop out at the bottom here and tell you what the weighting is on parts of the question and parts of the answer.
Right.
And then that feeds into
Right.
the later answers.
Right. So that's another good. So even P is constant, right? Because even P is constant because this entire representation depends on Q and A. So this matrix itself is dynamic. Then after you doing pooling, it's also become dynamic. You have to solve the max is dynamic. So if you interpret it as attention, these two parts are dependent on Q and A. So it's not a constant.
So essentially what this is doing is, what P is doing is saying, let's say I take the second word in the question and the fifth word in the answer. You take the representation from the top, the Q con and the A con, and P simply tells you based on those two, how much attention to pay to that
Right.
question word
Right.
and answer word together.
Right.
That goes into that cell of the matrix. That's what P does for you.
Right,
And
exactly.
once that's done, you do max pooling on the rows to figure
Right.
out what
Right.
you should pay attention to in the answer,
Right.
and then
Right.
otherwise to be.
Right. You got it. But the benefit here is that you're not only learning this P, you're also learning how to represent the Q and the A with respect to this P, right?
Right, you're learning the-
Right, exactly. So they're interacting with each other. So what is Q, A, P are interacting with each other. Right. So that we have evidence. For example, I can mention this now. When we do this kind of learning, we follow the same mechanism. For example, we do QACN, both are CN side. What we found out here that if you do this attention mechanism, you actually can use 10% of parameters to train a performance that's much better than using more filters. Because this model will focus you only pay attention to this part of the question or answer, but the most relevant to each other. Other parts you don't care. You don't need to learn very good filters there. So this ends up with a system that is not only more accurate, but with 10% of parameters and the training 2 times faster.
Let me ask you a question. In your training data,
Yeah.
is it the case that in the candidate answer pool for one question,
Yeah.
there is a candidate answer which is not the right answer for this question, but it's the right answer for some other question? So it's going to appear in another pool, and there is going to be the right answer.
Yes. Yes.
Is that the case?
That's the case. So basically, our pool is the following. So the pool including competing answers to this question, so which means there are also good answers, but not as good as this ground truth. They're also including some random answers from other questions. So which in that case, they go to other questions. So that's why it makes the task is actually kind of interesting and challenging. You need to distinguish both totally relevant answers and also relevant answers, but not as good as this one. Okay. Right, so now let me show you some results. So we actually put this paper out on arXiv. You can read more details about this in the arXiv paper. So I think a shorter story here is that for checker QA, this actually, that's almost as good as our, attention QA, LSTM, or map, but better on MRR. For insurance QA, they are more comparable. I think the reason is the following, right? So this model, as I told you, requires much less parameters. So when you train a task like a track QA with much less training data, the advantage is very obvious. You can do better than all other models we have seen. But when you have lots of training data, so one-way attention actually can kind of catch up. Okay? All right, so let me also show you one thing you want to expect here is that because you can do two-way attention, you probably can do better on find the good answers that is much longer, right? So usually the challenge here, the longer the answer, it's very hard to identify it's a good answer or not because I can collect so much more information. So that's what exactly what we observed here. So in this plot, we show you the blue line is the conventional standard, QACN model without any attention mechanism. So and the red one is our, two-way attention, APCN. Is that you can see that, it's reversed. Attention model is blue line. So you can see that, when the answer gets longer, the QACN performance drops almost linearly, The longer the answer, it becomes harder to find which one's the better one. But for, with the two-way attention mechanism, you can see the accuracy is more or less stable, even when the answer gets longer and longer. Okay? So I think that's what we expected. I'll show you some visualization example, right? So this is a typical insurance question we got. How much do a pool add to the home insurance? So this heat map shows you how these questions are also being aligned using attention mechanism. These are two attention mechanisms. So, question? Sorry, can you louder speak up? For this task. So we do not do that plot versus how performance varies with respect to the amount of training data. But what I can show you is this, right? So this track QA has only 1,000 training instances. Insurance QA has 10,000. Say it again. 1,000 question with the ground truth label. What's the right answer? And the competing answer. So 1,000 instances like that. The second task is 12,000. So it's much larger. But those tasks is more challenging. So I don't think this can tell you much. The point I want to make here is that we believe that using two-way attention mechanism, you have a chance to do better on smaller training data. Well, that's an open question, yes. I don't know. I wish I know. Okay, we'll show this. Okay, this is the attention mechanism. So I think, that's a reasonable good job to focus on the parts is important and the equal parts are not important. So you can see this both ways, For example, we ignore the do word in the question side. I don't know why we ignore the home, because maybe by poor is implied. I don't know.
Well, if I understand the architecture right,
Yeah.
home is not highlighted because it didn't match well against anything in the entire corpus. Is that
In
right?
the answer, yes.
Not because of the softmax.
Yes.
So insurance and pool did well in the softmax. They seem to be relevant
Exactly.
to
Right.
something.
Right. Exactly.
Or something seems to be relevant.
Exactly. For example, it could be redundant in this task because all the questions asking about the home insurance. You ask home. So that's why they figure out home itself is not important. Right. Very good. All right. So some more comments on two-way attention mechanism. Right. So we actually do this not only for CM, we also do this for LSTM. So the point is this: the representation of a question and answer here doesn't matter. Right? If you should look at this one, the Q&A can come from different representations. It doesn't matter. So we show that as long as you do two-way attention mechanism, this will help. The second comment I want to make here is that with this two-way attention mechanism, we can use much less parameters. I already mentioned that, but to be more concrete, we can use 400 filters to achieve same accuracy using 4,000 filters for regular CN, and the training time is 2 times faster. We are also applying this thing to other applications. This basic idea can be applied to any pairwise classification ranking problem. It doesn't have to be NLP or QA, right? So we have applied this to computer vision and bioinformatics tasks. We have papers to be submitted in this space. Okay, so these are some examples. What kind of best answer you can find from the deep learning models, right? So this is can you borrow against the global life insurance? So you can see top one answer we found from our system is the most useful one. Top two is the less useful one. But if you look at it, both are good answers. So that's exactly our challenge in this task. You want to identify the best answer for them, not only just find a good one. Okay, so I have only 5 minutes, so I want to scratch the surface on the category 3 about some work we did, but I don't have enough time, so I will only tell you some high-level ideas. So one of the challenges I told you here is that for category 3 is that you don't have an answer existing anywhere, so you need to come up with an answer, right? So this is basically a task saying I know what relevant information, pieces of passages. Now I come up with an answer that is consumable to the people in the loop, for the people asking the question. So a task we are trying to do now here is that how do I compress incoming passage into concise answers? So this is more like we call it abstractive summarization task, right? So it's not extractive. You are abstractive. You're generating from scratch. So we have some work in this space. I think I will not mention details. So it's basically encoder decoder framework, like many people are doing here, sequence learning. But the one thing we have innovation here is that we actually have something, combining generation versus copy. But we always have a model point back to original sequence to copy the subset of the input to the output. So we don't always generate all the time. Okay, that's one innovation. Another innovation is we're also doing hierarchical attention. I'm not going to talk more about details, but let me show you some examples. Well, first of all, we did some comparison with the most recent, work in this space from Facebook. They have a paper at the EMLP. I think, from these numbers we show here, we are doing much better in terms of this evaluation metrics. This is from a gigawatt corpus summarization task. Right, but let me show you this example, right? So this is a real news document we see there. And then the second row here is a golden summary, and the third is our, deep learning-based abstractive generation model. So a couple of things to notice, right? So we're pretty good at identifying the entities, which is important for getting a good answer. And we also come up with, interesting verb, which is not existing in the original document. So that's why what I meant by abstractive summary versus extractive summary. Okay, so the next part, very quickly, let me cover on the reasoning part, right? So for the third category, what we are doing here now is that we are trying to do an end-to-end learnable system that I can, consume all the background knowledge. When I take a question, I will derive an answer. So my training data will be only question and answer. All other things is hidden. So I want to build a system that can end-to-end differentiable. So this is a long-term goal. We are nowhere close. But a lot of people are working in this space. I'm sure you guys are working on this space as well. So including our colleagues from DeepMind and also from Facebook. Right? For example, neural tooling machine is one architecture trying to achieve this goal, although we are far away from that. So far, the only thing we see successful is learning copy strings. not close to QA. But even for this framework, we did some research. I think we found this very interesting. I think it's also making sense if you think about it from a cognitive perspective, right? So in the neural network machine, if you see from the picture here, right? So as a special example, they have a LSTM as a controller. They have an external memory matrix to store external information. So this matrix they have here is a vector, a matrix of vectors. So it's a linear structure. And given the linear structure, you cannot expand them too much, right? Because otherwise it's too slow to converge. And also they need to make them differentiable. So the addressing function needs to be differentiable. So all this adds constraints to how you can represent the information in your memory. So we have an insight here is that not all memory are equal, right? So it's very simple, right? My long-term beliefs should not change dynamically while I look up something new, right? So the neural network machine idea or any other end-to-end differentiable models should be based on this assumption. So I have a memory or my knowledge. When I read something, I do some addressing, I update my information in my memory. But to make it end-to-end differentiable, you have to look at the entire span, right? So with different weights. But that's expensive and unnecessary. So our insight here is that our long-term belief should not be changed upon I read something now. For example, if I believe the Earth is round, I'm not going to change my belief when I read the weather forecast saying tomorrow going to rain. This is irrelevant to my long-term belief the Earth is round. So the insight here is that we actually propose a structured memory structure. So we actually we want to hide some memory from the controller. And this long-term memory to represent the long-term knowledge and the common belief. This long-term part will only change when I see sufficient evidence in the short-term memory. So this will be triggered only by short-term memory updates, not by every reading inputs. So that's some paper we put out last year in NIPS RAMS workshop that focusing on reasoning on using end-to-end differentiable machine to learn to read. So this is we try different architectures here. Right, for example, one architecture here is that although my long-term memory is readable to my LSTM, but it's not readable by my right head. Right head will only affect me after this thing being triggered, after sufficient evidence. So we talk about the different architectures in the paper. We explore the 4 architectures. So I hope this makes sense to you, intuitively. But in practice, what we found here is that this actually makes training much faster. Right? I mentioned to you that we have been replicating NTM work for copy strings, but when we try to do QA task, vanilla NTM is very hard to converge. But when we introduce this structured memory, you can see from here, we actually converge much faster. Only after a couple of epochs, we are converging on this AI complete task. Okay, I think I'm over time for 2 minutes. So, but I want to say thank you for having me here again. And I tried to work last night on this graph, change to big data to question answering, but I think I'm not good enough with Photoshop. So I just do this. But anyway, so everybody should think about what could question answering do for you. All right, thank you.
So I am a little curious about whether question answering is enough. There's often follow-up questions. So question answering is usually formulated as a one-shot exchange for everything.
Right, exactly. So that's exactly, we also, in addition to question answer, we're also working on dialogue, right? So we actually have a debate. Should I consider dialogue a special case of question answering? Like you said, dialogue just follow-up questions. Or people should think about everything is dialogue. Question answering is a special case for that. But me and David Naham always have this debate because he's leading dialogue team, I'm leading QA team, but we work together. Anyway, so very good question. So what we are doing now is we're actually using lots of reinforcement learning to actually combining question answering together. So some of the simple apps we put out there from Watson is actually combining the dialogue and the natural language classifier to build a QA system. So using the NLC actually classifier to determine dialog states. So the list can be combined for sure, yes.
So a related question, the dialog state reflects some of what you know about the user's intentions.
Right.
You might also have other information about the user, maybe structured information.
Right.
They're asking about home insurance. They say, there was that question,
Right.
can Medicare cover my spouse?
Right.
Maybe you actually know something about this person.
Exactly.
And
Exactly. Right.
I wonder if that can help you do better question answering.
Oh, absolutely. That's a very good point. That's also part of the point I wanted to make, but I forgot to make it on the category 3. Category 3 for QA is that you actually need to consider the human in the loop, right? So that's why I say QA is AI for IA. You actually need to factor in who is this guy asking this question. I mean, that's why it's different from search. So if I ask me a question, I point to a knowledge source. I might be knowledgeable, but I'm not insightful. What's really insightful here is that people ask me a question, I consider who you are, provide the right answer to you. For example, if my kid and my boss ask me the same question, my answer might be different, right? So that's exactly you need to factor this in. So that's why that's category 3, yes.
And in your vision for enterprise QA, do you think that this might depend on the roles in the organization of the person asking the question?
Yes, that's something we are thinking of, because again, so we are not building. I mean, we have two missions. One mission is, like you said, we're building enterprise QA for some vertical industry, like for example, healthcare QA. In that way, it's on our shoulder how to model that. That's something we are still discussing about it. Another thing here is that we are enabling other guys building QA, right? So we need to provide this tooling for them to factor this in. For example, one way to do this here is that we are capturing this dialog states. Dialog states will link you to your end user profile. So you can use that profile to model that for developers. But this is still a very good question. I can even extend that, right? So it's not only depending on who are asking this question, also depending on how you're asking this question. For example, if you ask me a question that's similar, I can elaborate. But if you ask me the same question in the elevator, I need to give you an elevator pitch because you're gonna get to your floor in 2 seconds. My answer has to be short. So this is all kind of thing can have dynamics, affecting QA. That's why, as I said, QA is a very complex problem. It's very broad. I truly believe we are just scratching the surface here. Okay.
Let's thank Bowen again.
All right. Thank you.